Hi, welcome to my channel Industry 4.0. Today, in this video, we will understand the concept of ownership in Rust programming. Also, know the rules of ownership in detail. Please like and share the video and subscribe to my channel. So, let's start the video. Rust guarantees memory safety with a feature called ownership. Ownership works differently from a garbage collector in other languages because it simply consists of a set of rules that the compiler needs to check at compile time. The compiler will not compile if ownership rules are not followed. The borrow checker is a compiler component that ensures the code follows ownership. Ownership concept. Memory and allocation. Data can be stored either in stack or heap memory in Rust. Memory types. 1. Stack memory. 2. Heap memory. What are the stack and the heap? The stack and heap are both memory storage segments that are available for our code to use at runtime. For most programming languages, developers are not typically concerned about how memory allocation goes on the stack and heap. However, because Rust is a system programming language, how values are stored in the stack or heap is essential to how the language behaves. Stack and heap are parts of memory to be used at runtime, but they are structured in different ways. Stack. It collects values in the order it gets them and removes the values in the opposite order. Referred to as last in, first out, LIFO. Stack example. Think of a stack of plates. When we put more plates, we add them on the top of the pile, and when we required a plate, we take one off the top. Putting or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack. Removing data is called popping off the stack. Stack memory is an organized memory. It is faster than the heap memory due to the way it accesses the memory. All data gathered on the stack must have a known, fixed size. Stack push and pop example. Stack in action. Stack, how it works. The code then calls a function, the values move into the function, including, potentially, pointers to data on the heap, and the function's local variables get pushed onto the stack. When the function ends, those values get popped off the stack. Heap. The heap is less organized. Requested from OS. Slower. Follow pointer. A huge amount, take time to manage data in the heap. The data with a size that is unknown at compile time or size that might change must be kept on the heap. Heap allocation. When we put data on the heap, we say for some amount of space from OS. The operating system gets an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of that location. Why pushing to the stack is faster than allocating on the heap? Because the operating system has not to search for a place to store new data, that location is always at the top of the stack. Why accessing data to the heap is slower than allocating on the stack? Allocating space on the heap needs more work because you ask for some amount of space to the operating system every time. OS has to follow the pointer every time. Ownership. All programs have to find the way they use a computer's memory while running. Some languages have kept garbage collection that constantly looks for no longer used memory as the program runs. The programmer must explicitly allocate and free the memory in other languages. Rust uses a third approach wherein memory is kept through a system of ownership. Ownership is managed with a set of defined rules that the compiler checks at compile time. Ownership is the forwarding of a currently possessed entity to another party which causes the previous owner to no longer have access to the object that is being transferred. There are very clear rules about which piece of code owns a resource in Rust. It's the block of code that created the object representing the resource in the simplest case. In the last of the block, the object is destroyed and the resource is released. One of the ownership features slows down our program while it's running. In simple words for understanding purpose. Example: fn main / s is not valid here. It's not yet declared. Let s equals hello. / s is valid from this point forward. / do stuff with s. Println s. // This scope is finished, and s is no longer valid. In this example, the letter or variable s is the owner of the word hello and is valid from the point of declaration after the start of the parenthesis. And it exists valid until the end of the parenthesis. The Rust's unique feature is ownership, which enables it to make memory safety guarantees without needing a garbage collector. Why ownership? Maintaining a record of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so that we don't run out of space are all problems that ownership addresses. All primitive data types, integers, booleans, string literals, and pointers, address of heap data, are stored and kept on a stack, whereas for more complicated data types we have a heap. Ownership rules. Rule number 1. Each value in Rust has a variable that's known as its owner. Example: let a equals hello world. Variable value. In this example, the variable i.ea is also the owner of the value hello world. Rule number 2. There must only be one owner at a time. Example: let b equals string of from hello. Here variable b is the owner. Let c equals d. Here the value of c is moved to variable d, which now becomes the owner of hello. Understanding both variables a and b are within the same scope. Rule number 3. When the owner went out of scope, so does the value. Example: fn main, b is not valid here, it's not yet declared. Let a equals hello. B is valid from this point forward. Do stuff with b. This scope is now over and b is no longer valid. Fn main. B is not valid here, it's not yet declared. Let a equals hello. B is valid from this point forward. Do stuff with b. This scope is now over and b is no longer valid.